friends, today we are going to deal with something called as the chemical properties of haloalkane. So this is part 3 of haloalkanes, and I am Mr. Chutke helping you out with your chemistry. Okay, so chemical properties of haloalkane. Now in the previous section we have seen how we can prepare haloalkanes. Okay, how we can prepare haloalkanes. So we have used different methods to prepare haloalkanes. Like we have seen how to use symmetrical and asymmetrical alkenes to convert by adding HBr to convert it into haloalkane, alkenes to haloalkanes. We have seen alkanes to haloalkane. Then we have also seen Schwartz reaction, Finkelstein reaction, with help of which halogen exchange we can convert it into what? Haloalkanes. Apart from all this, we have also seen one more reaction, that is from alcohols. Now, what did we do in preparation? We used alcohols and converted it into haloalkanes. Now, what are we going to do? Okay, we're going to do exactly vice versa. That means in chemical properties, in preparation, we were preparing haloalkanes on the right hand side. Now, all the reactions in which I just mentioned, in all those reactions, we prepared haloalkane on the right hand side. Now we are going to take this haloalkane on the left hand side. In chemical properties, what are we going to do is we're going to take haloalkanes on the left hand side and we're going to see what different products can be obtained by using haloalkane. Okay, so earlier we had converted alcohol to haloalkane, but right now, because it's chemical properties, I'm going to convert haloalkane to alcohol. Let's see how I can convert haloalkane to alcohol. So if I want to convert haloalkane to alcohol, I can use KOH. The KOH should be aqueous, right? And I will get what? ROH plus KX. ROH plus KX. That's what I'm going to get. Basically, nothing is happening. K and X combine to form KX, and R and OH have combined with each other to form alcohol. So what have we done? We have converted haloalkane to alcohol. So now in this reaction we were able to do that. Let me take an example of this one. CH3CH2Br, okay, plus KOH. Now why I wanted to show you in separately is because it depends upon what you dissolve KOH in. Okay, whether you're dissolving KOH in water. If you're dissolving it in water, it's going to form an aqueous solution. And if you're dissolving KOH, the same KOH in alcohol, then you're going to form alcoholic KOH. Okay, and just because of the solvent of KOH, the two products which are formed get completely changed. Okay, so if you have dissolved KOH in water, that is aqueous KOH. See, reactants are the same, but products are going to be completely different just based on what? Just based on what you dissolve KOH in. What is the solvent for KOH? Okay, so here we are having aqueous KOH, here we are having alcoholic KOH. Okay, so what's going to happen in both the cases? K and Br is going to combine to form K and KBr, that is potassium bromide. Okay, that is what? Potassium bromide. So once potassium bromide combines, OH will get attached over here when KOH is dissolved in water. Okay, when it is aqueous. So we will be getting CH3CH2OH. That's nothing but ethanol. What it is? Ethanol. Okay, so again, when KOH is dissolved in alcohol and not in water, then K and Br will combine to form KBr, but at the same time, this H from here, one hydrogen from here, one OH from here, are going to combine with each other to form what? H2O. And what are we going to get is this CH3 single bond CH3 will convert into CH2 double bond CH2. That's nothing but ethene, and that's an alkene. Can you see the difference of the products obtained over here? Reactants were identical. In both the cases, reactants were identical. Haloalkane plus KOH. But depends on what KOH is dissolved in. If it is dissolved in water, it will ionically react to form KBr and alcohol. It will undergo a nucleophilic substitution reaction. It is a substitution reaction. Substitution means replacement. I'd given you an example last time. Rohit Sharma substituted by Virat Kohli. That means what? Rohit Sharma is replaced by Virat Kohli. Okay, so KBr plus what? Alcohol you have got. You can see that this Br has been replaced. In place of this Br, who has come in place of this Br? OH has come in place of this Br. Okay, OH has come in place of this Br, but in the second case, it's not a substitution reaction. Here, it is an elimination reaction. Why is it an elimination reaction, and which type of elimination it is? This is removal of halogen as well as hydrogen. So it is dehydrohalogenation. Which type of elimination is it? Dehydrohalogenation is the type of elimination. Dehydrohalogenation. We have removed a hydrogen as well as a halogen. That's why D means removal. Dehydrohalogenation. And which type of substitution is this? This is a nucleophilic substitution. We're going to see that in detail. Okay, so this is a nucleophilic substitution. Okay, negative replaced by negative. So you get an alcohol, and when there is elimination, always in all elimination reactions, the single bond converts into a double bond, or the double will convert into a triple triple bond. That means the number of multiple bonds increase when it is elimination. So which type of elimination? Dehydrohalogenation. Okay, so here we have completed this reaction, but if you observe the first one, that is the substitution reaction, now there is a mechanism to it. Because why is it called as nucleophilic substitution? Because you can see over here that negative has been replaced by negative. Okay, negative has been replaced by negative. Replacement is there, but negative being replaced by negative, so it is called as nucleophilic substitution. What are we going to do is we're going to see a mechanism for this, that is SN2 and SN1 mechanism. First we'll move on to the SN2 mechanism. Okay, so SN2 mechanism, what does S stand for? S stands for substitution, and it's written a little inverse. Okay, nucleophilic. We'll come over here, nucleophilic substitution. What is a nucleophile, by the way? The one who attracts a nucleus. So the one who attracts a nucleus, it itself has to be negative. So nucleophile meaning negative. Nucleophilic substitution meaning negative replaced by negative. Electrophilic substitution will mean positive replaced by positive. And nucleophilic substitution will mean negative replaced by negative. So those children who are a little, confused, just have a look over here. Chemistry, organic chemistry reactions. Okay, organic chemistry reactions can be divided into these, right? We can have addition, we can have substitution, okay, we can have elimination, and we can have, tell me, rearrangement. Okay, so in addition, what is happening? The double bonds are converting into single bonds, or the triple bond is converting into a double bond. In substitution, what is happening? Substitution is what? Replacement. Substitution is what? Replacement. Elimination is what? Tell me, what is elimination? Elimination, when I told you that the single bond will convert into a double bond, just exactly opposite to addition. In addition, the number of multiple bonds decrease. In elimination, the number of multiple bonds increase. So double will convert into triple. So that is elimination. Types of elimination. Types of elimination are, there are actually many types: dehydrohalogenation, dehydration, decarboxylation, deamination, dephotophosphorylation. Many are there. Okay, many examples for elimination are there. Then in substitution, we are having two examples, two types. That is nucleophilic substitution. I can write SN over here, nucleophilic substitution, and electrophilic substitution. So in nucleophilic substitution also we are having two types, SN1 and SN2. So at the moment we are focusing on SN2, and then we'll focus on SN1. So these are the mechanism of nucleophilic substitution. Substitution mein do types, nucleophilic and electrophilic. Okay, so come here. Let's focus on nucleophilic substitution part 2. Okay, so if you ask me that what is the reaction? Reaction is very simple, just what we did. CH3OH or CH3Br is converting into, you are adding, say for example, OH minus in the form of KOH or in the form of anything, right? NaOH will also do, no problem. Okay, so you'll get CH3OH plus KBr. Now this is the reaction. We're going to see the mechanism for this reaction, right? Nucleophilic substitution, negative replaced by negative. You can see that negative has been replaced by negative. So let us see what the mechanism for SN2. So while writing the mechanism, I'm just going to take the ionic part. That means I did not take K over here. I will only take OH over here. OH minus is the nucleophile. Nucleophile having the negative charge. It's also our attacking agent. It's going to attack. And what is here? Br is here. So CH3Br, and this is your substrate. Okay, substrate is the molecule or the compound on which the nucleophile attacks. Okay, so this is your nucleophile. Now then what is going to happen is, initially this nucleophile is going to attack from the front side. So when nucleophile is attacking from the front side, what is going to happen? There is going to be repulsion. Negative are going to repel. But when nucleophile attacks from the hind side or back end, then it will succeed. Why front side attack is not possible? Because negative are going to repel. Br is also negative, OH is also negative, both are going to repel each other, and therefore negative attack is a little difficult. But if front side attack is a little difficult, but from backside attack it's very much possible, because yahan par kaun hai? Halke phulke hydrogens hai. Halke phulke, I mean hydrogen is having an atomic mass number of only +1. 1. So if the atomic mass number is 1, the hydrogens will quickly move out of the way and allow OH to get attached. Okay, OH to get attached, and yahan pe Br is getting detached. OH is about to get attached, and Br is about to get detached. I hope you can see the dots, right? So this is a dotted line. What does this indicate? It indicates that OH is not completely attached, Br is not completely detached. Br is about to detach, OH is about to attach. Just like, say for example, you are walking out of the house. So when you are walking out of the house, आपके घर के दरवाजे पर एक, जिसको हम लोग कहते हैं दहलीज, okay, so you keep one foot outside the door and one foot is inside the door. So what is happening? You are not completely outside, you're moving outside, but you're not completely outside and you're not completely inside. So that is something called as transition. Okay, that is what transition meaning you are not, you are in between. Like the transition for day and night will be evening, or what do you call it, a dawn dusk. Okay, so that is what transition. Okay, simple example, you have milk and you are white colored milk, you are pouring roux afza syrup in it. Roux afza is red in color, so white and red color you are mixing. So when you are mixing white and red color, what's going to happen? It's going to form a pink color. So what is pink? Pink is a transition color. Pink is a transition color. It's not completely white, it's having a little bit of whitishness, but it's not completely white. And it is having a little bit of reddishness, but it is not completely red, it is in between, it is pink. So pink is transition. Okay, similarly this is also transition state. It's not completely an alcohol, nor is it an haloalkane at the moment. Okay, and because both the groups are in touch, so this is transition state and this is highly unstable. You can see over here that they are what, highly unstable. Okay, why they are highly unstable? Because valency of carbon is what, 5. Valency of carbon 5 is the valency of what, carbon over here, but it is unstable. So this transition state, then now what is going to happen is Br is completely going to get detached and OH will completely get attached. So what are we going to get? Yeah, what are we going to get over here? Have a look. We are going to get OH. OH will get completely attached over here. We're going to get an alcohol, methanol, and hydrogens will again change their position. If you observe the position of hydrogens over here, the position of hydrogens over here is like this. And the position of hydrogens, which was here, I'll just zoom out a little. Yeah, so the position of hydrogens over here is like this. So if you can see, it's like an umbrella. The umbrella was open over here. Okay, and you pulled the umbrella, so all the points came to the other direction, and that's why the position of hydrogen is like this. So it's often known as the umbrella effect. What this part is also can also be called as umbrella effect. Well, in your book it must be written as inversion effect. This umbrella effect word is coming from Morrison and Boyd, a reference book for organic chemistry. Okay, so inversion effect or umbrella effect. Why umbrella? Because the hydrogens look like an open umbrella, and when you pull it, the hydrogens come to the other side, the points of the umbrella come to the other side. So that is what umbrella effect. Okay, so this is SN2 mechanism. Now we need to draw something called as the EPD of the SN2 mechanism. Now what is EPD? Let's see. EPD, energy profile diagram. Yeah, energy profile diagram for SN2 mechanism. So for SN2 mechanism, we have the reactants which are having a certain amount of energy, and then you get the products. So basically here we are having energy. It's an energy versus time of reaction, or you can time required for the reaction, or you can say progress of reaction. Okay, time or progress of reaction. So you can see over here that this is the energy of the reactants. The energy of the reactants is a little higher as compared to the energy of the products. And when you can see, actually it's not a proper bell-shaped graph. Let me draw it again, just a second. Yeah, this is better. So this is the energy of reactants, this is the energy of products. Okay, so you can see that the energy of reactants is a little higher as compared to the energy of products. Why? Because the energy of reactants is higher, that means it's a little unstable. I always give this example that if there is a small boy, he's having a lot of energy, he will always keep on doing something or the other. He will be up to something, he'll pull the threads of the carpet, or he may pull your hair, he'll do something or the other. But because why? Because he's having high energy. Higher energy results in instability. On the other hand, on the contrary, we are having an old man, right? Old man, he's quietly sitting in one place, maybe watching TV. Okay, so he will not move much. He's not very unstable. He's stable because he's having low energy. So products are having low energy. That's why they are a little less reactive. Reactants are having higher energy because they are more reactive. So what's going to happen is here you can see that the amount of energy which is given to the reactants to form something called as transition state. The transition state is the peak of energy. What it is? It is the peak of energy. So transition state, I told you, it was unstable, and obviously if it was unstable, the energy would definitely be much higher. So for every reactant to convert into product, you need to supply this energy, and this energy is called as the activation energy. What it is called as? Activation energy. This energy is called as activation energy. And if you want to reduce this activation energy, then you need to use a catalyst. Catalyst will perform the same reaction with lower activation energy. So this is with catalyst. Okay, and this is without catalyst. So without catalyst, you see over here that you are requiring more energy, and with catalyst you can see that you are requiring lesser energy. So with catalyst, your reaction will simply go and it will become faster because you did not provide or supply so much of activation energy. With a lower activation energy, you will be able to get your product. Okay, you will be able to get your product. Okay, so this is the EPD, energy profile diagram, for SN2 mechanism. Okay, and the reaction is also very simple. We have seen that. Now let's move on towards SN1 mechanism. Now SN1 mechanism, see, SN2 mechanism is generally used for primary and secondary haloalkanes, but SN1 mechanism is used for, if you don't know what is primary and secondary, go to part 1 and watch the classification of haloalkanes. You'll understand what is primary and secondary. And SN1 is used generally for tertiary haloalkanes. Okay, so all these questions are asked in your exam. Okay, that's why I'm mentioning it separately. So this is a tertiary haloalkane because this carbon is attached to 3 other carbons, and halogen is attached to that carbon, which is in turn attached to 3 other carbons. So I'll again take a Br, I'll again take an OH over here. So this is the nucleophile again, and okay, this is the nucleophile, and this is your substrate. Substrate is the place where nucleophile is going to attack. Okay, so this is going to be step 1. This reaction is in 2 different steps, 2 distinct steps, unlike SN2 mechanism. Okay, so OH minus will again try to attack from the front side, which is again and not a success. Why is not a success? Because OH minus and Br minus both are negative, negative will repel. In the previous case, backside attack was possible, but now, to your surprise, even the backside attack is not possible. Why? Earlier, in case of SN2 mechanism, you can see over here that there were halke bulke hydrogens, okay, who were able to change their position. Okay, hydrogens were having atomic mass number 1. They were able to change. They got scared. They were able to change the position. But if in case of SN1 mechanism, in SN2 it was like that. In SN1 you are having bulky groups CH3. Atomic mass number of hydrogen is 1. Atomic mass number of CH3 is 15. So they are bulkier as compared to hydrogen, and they are not going to change their position. They are not going to leave their position. So bichara OH, it is having nothing in its hand at the moment. Okay, OH के हाथ में कुछ भी नहीं है, ना front side attack है, ना back side attack है. It is pitiable. Who? OH. So nucleophile here in this reaction does not matter at all whether the nucleophile is there or not there. Why? Because it's not able to attack from the front side, not from the back side. So इसका existence कोई मायने नहीं रखता है. It is not important here. And whether you use a strong nucleophile or a weak nucleophile, that also does not matter. Why? Because nucleophile is just not able to attack. So the strength of nucleophile here does not matter, unlike which was mattering in SN2 mechanism. Here it is not mattering at all. What? The strength or how strong is the nucleophile. Here it does not matter. So sir, then what to do now? Right, front side attack possible nahi, back side attack possible nahi. So we have nothing to do. I mean, OH has nothing to do in its hand unless and until, I mean, only to wait. Okay, it can only wait for the C and Br bond to break. And moreover, this C and Br bond is pretty difficult to break. Why it is very difficult to break? Because these carbons are electron donating groups. So this carbon becomes, this obviously alkyl groups are electron donating groups. This carbon becomes electron rich. This electron rich carbon, and Br is electron deficient. What is Br? Br is electron deficient. So electron rich carbon and electron deficient Br will not leave each other. Okay, just like an poor friend will not leave his rich friend. Okay, a poor person is not going to leave his rich friend because he's getting supplies from him. Okay, so Br is getting electrons. Br is electron deficient. It's getting electrons from this carbon, electron rich carbon. So Br would never like to leave this carbon. Okay, and in this kind of situation, now this becomes the slowest step. Okay, it's a very slow step, and because it is a slow step meaning it is the rate determining step. All slowest steps are the rate determining step. Okay, the rate is determined by the slowest step. Okay, rate of a reaction, or say for example, if you want to go for a marriage, okay, और 15-20 लोग हैं, सबको मैरिज में जाना है एक बस में बैठ के, तो सबको लिए बिना बस निकलेगी नहीं. और जो लास्ट पर्सन आएगा, जो लेट आएगा, जो सबसे स्लो, ज्यादा टाइम ले रहा है तैयार होने में, ओके, सो जो सबसे लास्ट आएगा उसके ऊपर डिपेंड करेगा कि हम लोग कितना जल्दी पहुंचेंगे, राइट। अगर वो जल्दी आ गया, जो लास्ट पर्सन है, जो स्लोएस्ट, 2-2 घंटा लेट कर रहा है, वो अगर 1 घंटा जल्दी आ गया तो हम लोग 1 घंटा जल्दी पहुंचेंगे। अगर उसने और 1 घंटा लेट कर दिया तो हम लोग और 1 घंटा लेट पहुंचेंगे। सो हमारा रेट ऑफ रिएक्शन किसके ऊपर डिपेंड कर रहा है? वो लास्ट पर्सन के ऊपर, वो स्लोएस्ट पर्सन के ऊपर। सो वैसे ही जो स्लोएस्ट स्टेप है, स्लोएस्ट स्टेप के ऊपर रेट डिटरमाइन करता है, राइट। रेट डिपेंड करता है कि ये जितना फास्ट होगा उतना रिएक्शन, पूरी रिएक्शन फास्ट हो जाएगी। ये रिएक्शन जितना स्लो होगा उतना पूरी रिएक्शन को टाइम लगेगा। ओके, सो now this is what the slowest step. Slowest step is the rate determining step. I hope you have understood. Now just like we put NaCl in water and it dissociates, although it is having good forces of attraction, there are strong forces of attraction between Na plus and Cl minus, and when NaCl put in water it dissociates. Like that only these two are, we are hoping that they dissociate, and it will take some time to dissociate, and after it dissociates we are going to get CH3CCH3 with carbon with a positive sign, and Br minus has been, it has left over here. Okay, Br minus is gone. So finally, after a lot of time and with a lot of difficulty, Br has dissociated. Now in next step, now this was step 1. Now in step 2, what's going to happen? In step 2 we are having your CH3CCH3 and CH3. Okay, now it's having a plus sign over here. That means it's electron deficient. Br has gone along with its electron, and now we are having OH minus, which is a nucleophile, electron rich. Now this electron rich center will attract or will attack and get attracted and get attached to electron deficient center. Negative attracts positive, unlike charges attract each other. So quickly OH minus will get attached over here, and without taking much time, this OH will get attached over here. So this is a fast step. What it is? It is a fast step. And what have you got? You have got isobutanol. You can also call it as 2-methyl propan 2-all. Okay, so this is step 2 is fast, step 1 is slow. Okay, so this is your entire SN1 mechanism. SN1 full form, nucleophilic substitution unimolecular. Previous case SN2 mechanism, nucleophilic substitution bimolecular, and this one is unimolecular. So how is the graph going to be? The graph or the energy profile diagram is going to be something like this. Have a look. So energy profile diagram, let's see. So in this energy profile diagram, again the reactants are going to have a greater energy than the products, but here we are going to have two transition states. We are having transition state 1 and transition state 2. Obviously the graph is again same graph, I mean energy versus progress of reaction, same x and y axis, progress of reaction. Okay, so you're getting two transition state. Here is reactants. You're supplying what? Activation energy for them to increase the energy, reach up to the transition state. So why are you supplying energy? So that, see, if you don't supply energy, the reactants won't collide. They will not bombard on each other. And unless and until they don't bombard on each other, they don't collide on each other, unless and until there are fruitful collisions, okay, the reaction is not going to take place. Okay, if there are no fruitful collisions, the reaction is not going to take place. So if you want the reaction to take place, you need to allow it to undergo fruitful collisions. For that, you need to supply energy. Okay, and that energy is only called as the activation energy. We can supply thermal energy. Because of supplying thermal energy, what will happen? The thermal energy will convert into kinetic energy, allow the bombardment, and then you will get what? The products. So reactants, we supply energy to the reaction. We got two transitions. Now why we got two transition states? Because this is a two-step reaction. In the first step, the energy increased when Br was leaving. When Br was leaving, the energy increased. And the second step, OH was getting attached. When OH came closer in the proximity of the carbocation or the positively charged carbon, we formed TS2. TS2 is what? Transition state 2. And finally, the energy dropped and we got stable products. Okay. So this, for those who don't know, this carbon is called as carbocation. And remember that the tertiary carbocation is the most stable as compared to the secondary, as compared to the primary. Tertiary carbocation is having 3 electron donating groups. Okay, and because it is having 3 electron donating groups, this carbon becomes stable. See, अगर आपको जल जाता है, ठीक है, if you get a burn on your skin, okay, if you apply ice, you feel it's better. Okay, but if I make you sit near the heater, or if you put an iron or if you move close to the burner, will you feel better? No, right? So similarly here, when it is got burnt, that means its electron is lost. If you apply electron donating groups, okay, that is, it will feel cool, it will feel better. So tertiary has 3 electron donating groups, secondary has 2 electron donating groups, primary has 1 electron donating group, so it's the least stable. And what will be more unstable than this, if you attach an electron withdrawing group to this. For example, if I attach an NO2 over here, or C double bond O group over here, or S double bond O group over here, so this is going to suffer like anything. Why? Because एक तो पहले से इलेक्ट्रॉन डेफिशिएंट है, एक तो पहले से उसने इलेक्ट्रॉन खोए हैं, और उसमें आप उसके और इलेक्ट्रॉन्स खींच रहे हो, और इलेक्ट्रॉन विड्रॉइंग ग्रुप अटैच कर रहे हो, और उसको तकलीफ होगी, राइट? आपको जला है, और मैं उस जले के ऊपर नमक छिड़क रहा हूं, या उसको मैं फायर के नजदीक लेके जा रहा हूं, सो दैट इज गोइंग टू बी electron withdrawing group. Electron withdrawing groups are going to harm. Okay, understood till here? I hope we have covered SN1 and SN2 mechanism till here, and we have seen the reaction as well. Okay, so SN1 and SN2 mechanism. Now all our chemical properties, most of our chemical property reactions will depend on these two mechanisms, SN1 and SN2 mechanism.